Welcome to Biomaterials. What are we going to talk about today? Today we're going to talk about degradation of polymers. And we're going to break up this lecture into a few parts. So first, we're going to talk about the two reaction types that lead to degradation. Or the two reaction processes, the two reactions of degradation. And the chemical reactions that lead to polymer degradation generally fall into one of two categories. They fall into hydrolysis or enzymatic degradation. And in particular, like I guess we're mostly talking about degradation of polymers within the body, but also these reactions can occur outside the body as well. And when we talk about hydrolysis versus enzymatic degradation, I'll give a bunch of examples of polymers. Some polymers which typically experience hydrolytic degradation, other ones which typically exhibit enzymatic degradation in the body. So examples of polymers that typically experience these. Then we'll talk a little bit about some typical reaction rates that we might expect to see out of different classes of polymers. So typical reaction rates. And it turns out that these reaction rates, depending on exactly what type of polymer you have, what chemistry, and then some other factors, the degradation rates of different polymers can span something like 8 orders of magnitude. And that's incredible, right? Like 8 orders of magnitude in terms of the time scale with which some polymers degrade compared to other ones. And this lends us huge flexibility. Sometimes we want polymers to degrade in a particular way, right, for release of drugs. Sometimes we want polymers to degrade at a moderate speed, for example, for tissue engineering scaffolds, where we sort of want it to eventually degrade but don't want it to degrade so fast that the body can't replace it with natural tissue in time. And then other types of polymers, upon implantation, we almost never want to degrade. For example, like the casing that surrounds a battery for a pacemaker, or some other type of kind of medical device implant. We want those to basically last as long as possible. And by selecting different polymers and understanding which polymers have higher reaction rates than others in terms of their degradation, that can inform the selection of materials. So I'll just kind of give some broad ranges for what these reaction rates might be. Then we're going to take a closer look at the chemistry of hydrolysis, and basically what factors lead to accelerated or slower hydrolytic degradation of polymers. And then sort of separate from the two reactions of degradation, we'll talk about two modes of degradation. And what do I mean by two modes of degradation? Well, it turns out that if you put a polymer in an environment when it degrades, there are some scenarios where basically the whole polymer starts degrading simultaneously. The middle, the outside, the whole thing basically degrades, kind of equally. It doesn't matter where you are. And then other types of polymers, when you put them in an environment, sort of erode from the surface, where they sort of gradually get smaller and smaller and smaller. You can almost imagine like the surface sort of receding towards the center. And those two modes of degradation, the first one that I described is called bulk, and we'll contrast that to surface degradation. The surface one being the one where the sort of surface recedes towards the center. The bulk kind of remains largely untouched until the surface gets to it, and then it degrades. And bulk, basically everything is degrading simultaneously, and sort of the whole material itself kind of gets weaker and weaker and weaker over time. And we'll sort of we'll describe these two phenomena qualitatively. But then it turns out that there's a quantitative metric that you can use to determine which of these modes you'll be in, and it's basically called the second Domkohler number. It's a parameter that you can use to help decide which of these modes you're likely to be in. And that's a parameter that allows us to predict which of these modes you'll be in. And then finally, after we take a look at the second Domkohler number and some of the factors that go into it, for example, the size, the diffusion of water, and the reaction rates, those factors all go into the second Domkohler number, we'll take a closer look at some at material chemistry. And how the material chemistry relates to its microstructure, which relates to water diffusion within the material, and ultimately how this relates to degradation rate, and basically how choosing the actual chemistry of the material can sort of have an effect on its degradation rate, sort of independent from the reaction rates, but how material chemistry can affect microstructure to sort of have an indirect effect on degradation rate. So let's dive into it. Let's talk about two reactions that lead to degradation: hydrolysis and enzymatic degradation. So hydrolysis is you can, if you look at sort of the etymology of this word, the hydro means water, and lysis typically means breaking or cleaving. So what is hydrolysis? It basically is a chemical degradation process of polymers by which water breaks the bond between polymer chains. And in a sense, this is kind of like the opposite. If you think about this, this is the opposite of condensation. Opposite of condensation, polymerization. Right? Well, remember, condensation, polymerization, two groups reacted together and kicked out of water. Hydrolysis is basically that process happening in reverse, where water comes back, reacts with the atoms that make up that polymer bond, and then those polymers sort of go back to the state that they were in before they reacted with one another. So it's sort of the undoing of condensation is hydrolysis. And so what polymers might be vulnerable to hydrolytic degradation? Well, the types of polymers that were formed via condensation. So often opposite of condensation, polymerization. So examples of polymers that were formed via hydrolysis include polyesters. So examples include polyesters. And some specific examples of polyesters include polyglycolic acid, polylactic acid, and polycaprolactone. So these are some polymers that degrade via hydrolysis, and in a sense, and all of these basically they're polyesters because they have this ester bond in them. So if you remember, an ester bond was basically something like this, where there's a carbon double bonded to an oxygen, which is single bonded to an oxygen, which is single bonded to a carbon that then sort of makes up the rest of the chain. And basically water can come in, and so if we have an H2O plus this, then this reaction essentially goes into reverse to sort of create a COOH and a COH right here. So this water comes in and cleaves this bond. And sort of all of these, exactly what happens in, these polymers all differ from one another in terms of what's between these ester bonds. Like polyglycolic acid has relatively few atoms between these bonds. Polycaprolactone has longer. But the key takeaway here is that, all of these have this ester bond, and this ester bond can react with water to basically split it apart. There are some other molecules that don't have exactly an ester bond, but have ester-like characteristics in their bonds. So while not a polyester exactly, polyurethane is a general class of molecules, and polyurethanes have things that look like this, where there's an N, H, C, O, O. And if you look at this polyurethane, this part of the polyurethane is ester-like, and therefore vulnerable to hydrolytic degradation in the same way that polyesters are. So these and this reaction with water and these ester bonds is spontaneous, basically. As long as the water's there, eventually some of the reactions can be fast, some of them can be slow, but eventually these reactions will occur, and eventually these bonds will break for both polyesters and polyurethanes. So the key thing is the degradation is spontaneous. It is spontaneous. It can be slow, can be fast or slow. But the key thing is that, as long as if you wait long enough in the presence of water, these things are going to break. We can contrast the way that polyesters and polyurethanes degrade to enzymatic. To enzymatic degradation, where basically there are enzymes in the body that cleave. Enzymes in the body that cleave bonds. Some of these enzymes, some of the enzymes might use water in that reaction to cleave the bond. But the key thing here is oftentimes these can happen quickly, where basically these enzymes sort of catalyze this reaction to happen faster. And a general principle is things that degrade via enzymatic degradation are things that are biopolymers, or things similar to biopolymers that our body naturally produces. So these are either molecules that our bodies make, on their own, or similar. So what do I mean by that? Well, our bodies make, for example, our bodies make polyamino acids. So polypeptides, or polyamino acids. Right? So, I eat some food. That food has some protein in it. My body wants to break down that protein into a bunch of amino acids, so then I can synthesize my own proteins that make up, my skin and muscles and everything else. So basically, because we evolved to be able to eat food and break down proteins, if we want to use proteins as part of biomaterials implants or biomaterial solution, our body already has a lot of these enzymes floating around that break down proteins. So, so these basically have chemical motifs that look like this, right? Here's the peptide bond, or the amide bond. Our bodies have enzymes that basically cleave this, and that enzyme uses a water in the process of cleaving this. But the key thing is that we have enzymes that catalyze the cleaving of this reaction. So some examples of polypeptides or polyamino acids that degrade enzymatically in our body are collagen, elastin, but even some artificial polyamino acids. So for example, poly-L-lysine is basically it's a polymer. No organisms on Earth make proteins purely just of one amino acid type, but we can synthesize L-lysine, and we can polymerize it in vitro. And even when you take this artificial polypeptide that's sort of like all the same type of amino acid and implant that into the body, eventually, like this can degrade basically by the same mechanism that these natural proteins do. Some polysaccharides degrade enzymatically. For example, like the polysaccharides that exist already in our own bodies, right? It would be pretty silly if our body made polysaccharides but then had no way to break them down after they were no longer useful. So some examples of polysaccharides that already exist naturally in our body that we break down by ourselves are hyaluronic acid, and chondroitin sulfate. Right? These are two polymers that we make. Then there are a couple of polymers that are similar enough to polysaccharides that exist in our body that can degrade via enzymatic degradation, which is chitosan. So we don't make, but is close enough for some of our enzymes to break it down. But then, for example, some polysaccharides that we don't have sufficiently effective enzymes include chitin and alginate. So take a moment now, pause and ponder, why might we lack enzymes to break these down? Well, I don't know about you, but I'm not an insect, and I'm not a plant. So I never evolved. There was never sufficient evolutionary pressure for me to have evolved enzymes to break down these. Basically, like, I might eat some bugs, but I got enough calories from the non-chitin part of the bugs where I never needed to break down chitin. And the same with alginate. I got enough calories from whatever other plants I was eating that my body didn't need to break down alginate. So basically, there was never enough of an evolutionary advantage for us to evolve enzymes to break these down. Whereas like these things that our body makes by itself, like we need enzymes to break these down. And then sometimes you just get lucky and your enzymes that already exist can break down some things like this. So what does it mean? Well, this actually provides some benefit to us in a bioengineering context. So for example, my spouse did some tissue engineering projects where she was making artificial intervertebral discs, and she made the sort of jelly-like center of the discs in between your vertebrae out of alginate, such that they would last long enough. Basically, like, because our bodies don't have enzymes that can break down alginate very quickly, that alginate construct could last long enough in order for it to sort of be effectively integrated with the host tissue. Whereas, for some other cases, maybe you want your implant to degrade very quickly, you might choose a polysaccharide that your body already has in it. For example, like wound dressings, there's some wound dressings that use chondroitin sulfate or hyaluronic acid because you want those to sort of degrade quickly as a surface wound heals. So that's some contrast. between the two reactions that involve degradation, hydrolysis or enzymatic reaction. So let's now take a look at some typical reaction rates, in particular for hydrolysis. So when we think of a reaction rate, I might think of this as something like, if I'm going from a bond, like a bond to the broken pieces, you might sort of, if you were to sort of model some of like the actual chemical kinetics, you might form this in terms of like reaction rates. And oftentimes when you form these reaction rates, the reaction rate is proportional to the concentration of the reactants. Right, so what this might, how might we form something like this? You might form something like d bonds dt, in that like this is the time rate of change of concentration of bonds is typically it's negative in the sense that we're losing bonds with time because it's a reactant, and basically this rate is proportional to the number of bonds that we have. In the same way that, like, if you have some radioactive element, the more uranium you have, the more likely at any given time one of those uranium atoms is going to decay. It's sort of the same with the bonds. The more bonds we have, the more the faster at any given time one of those bonds is going to become broken. So basically, the time rate of change of bonds is proportional to the amount that we have present, and sort of any time you have something like this, you can kind of put like a K effective in the front. So this is what we might call like a rate, a sort of effective rate constant. So the higher the K, then the faster these bonds are degrading. So take a moment now, pause and ponder. What are the units of K effective? If you're for example like working in SI, well, so concentration of bonds would be like a mole, per liter. And the time rate of change of that would be mole per liter per second, right? So mole. So the units on the left-hand side of the equation need to be the same as the units at the right-hand side of the equation. So K basically needs to have units of inverse seconds. So K basically has units of inverse seconds. Bonds has moles per liter, or concentration of bonds has moles per liter, and the time rate of change of that would be moles per liter per second. So these K has sort of units of inverse seconds. So if you want a sort of, it's not exactly true. There's a factor of like natural log 2 somewhere in there, but you can sort of think of K effective as like 1 over the half-life of a bond. You might think of K effective as sort of like 1 over the half-life, in that if it has a very long half-life, it's going to have a very low reaction rate constant. Or if it has a very high reaction rate constant, it's going to have a very small half-life. So what are some typical half-lives that you might see? We'll start with some of the smallest, the shortest half-life. Which basically have, I haven't actually outlined here, but this class of polymers called polyphosphazines, And these polyphosphazines have a K effective somewhere on the order of 10 to the minus 2 inverse seconds. It's less than K effective, which is less than like 10 to the minus 7th inverse seconds. And if you wanted to sort of put this in terms of like 1 over something that's like half-life, you know, this would be like 1 over 100 seconds. So, you know, on the order of minutes, polyphosphazines typically degrade. This 10 to the minus 7th is something on the order of like 1 over 100 days. Right, so you can have polyphosphazines that degrade on the order of minutes or on the order of months. Building up towards longer half-lives, polyurethanes and polyurethanes and polyesters, those have a K effective on the order of 10 to the minus 8th inverse seconds, which if you wanted to sort of put that in terms of something like 1 over half-life, would be on the order of like 1 over 3.2 years. And this is sort of, you know, for example, polyesters, the like compostable cutlery is is typically made out of polylactic acid, and you know you can compost those on the order of a couple of years, right? So rather than having plastics that last in the environment for centuries, your sort of compostable cutlery can degrade on the order of just a couple of years. And then some of the ones with the longest half-lives include polycarbonates. And these polycarbonates have a K effective on the order of 10 to the minus 10th inverse seconds, which if you wanted to sort of put that in terms of a half-life would sort of be like 1 over 317 years. So, which, you know, I want to live a long time. I don't think I'm going to live 3 centuries. So for example, you know, if you want something to sort of degrade very quickly, for example, for the purpose of drug delivery, you might want to use polyphosphazines. You know, if you want this drug to be delivered in minutes or weeks or months, something like that. If you want, for example, to create a scaffold for some tissue engineered thing where basically you have your scaffold and you want cells to eventually be able to break down that scaffold and replace it with native tissue, you might want something like this that has a K effective or a half-life on the order of, you know, months or years. And if you want something to be implanted and last forever, you know, then you might want something like polycarbonates, although polycarbonates have some other health concerns that will, you know, I've talked about in another lecture, that basically has these degradations that, you know, it takes centuries for it to degrade. So this, you know, and if you think about, you know, from order of minutes to the order of centuries, these degradation rates can span 8 orders of magnitude, which is amazing. And those reaction rates that I quoted are typical reaction rates for implantation inside the human body. And obviously, you know, different parts of the body and other factors, you know, tweak those potentially by orders of magnitude themselves, but just to sort of give you a rough idea of how biodegradable certain polymers may or may not be. You know, there we have it. So now let's take a closer look at the chemistry of hydrolysis. So what does hydrolysis look like? So when we formed, and in particular, we're going to do so for ester bonds, just as sort of a case study. So if you remember, ester bonds formed by the reaction of a carboxylic acid group, right? So we had one polymer chain with the carboxylic acid group, and then another with an OH group. These react when these reacted together in the forward reaction, which we would call polymerization. They reacted together to form COOC plus an H2O, so one H2O. But if you consider an H2O interacting with this bond here, they reacted in the reverse direction, which is what we would call degradation. So what are some factors that basically control this process here? We'll take a moment now, pause and ponder. What happens when we expose polyesters to water? Well, when we expose polyesters to water, if you increase the concentration of products, then you drive the equilibrium towards reactants. And if you increase the concentration of reactants, then you drive the equilibrium towards products, right? So what's the key thing here? We basically increase the concentration of products, and that basically drives the equilibrium to reactants. So basically, what does this do? This basically increases the speed of degradation. So what does this mean? Basically, if you have your compostable fork or whatever, and put it in, put it in your, moist composty soil, that's what causes that to degrade. Whereas that compostable fork, when it's kept in the relatively dry packaging, the little sleeve or the little box that it came in, it's only exposed to just a little bit of moisture from the air. So there we have it. Sometimes people who 3D print in polylactic acid or other polyesters need to keep their print filaments in a dry box, where it's basically a box, and they put those like little silica gel desiccants in the box, and basically that you don't want your 3D printing filament to start absorbing water and degrading prior to the printing process, because basically it messes up the processes and can ruin your print heads. It can ruin the tolerances of your prints and all that stuff. So basically, water is the enemy of polyesters. Water comes in, cracks that bond open, and then boom, you've degraded it. In terms of implants, hydrolytic degradation can be useful in some points. You create some medical device with polyester, and you implant that polyester thing into the body, and the body always you can pretty much always guarantee that, like, I don't know about the inside of you, but the inside of me, it's a pretty wet place, right? Our bodies are 70% water by mass, something like that. So if you put a polyester implant inside the body, you can always count on a very reliable amount of water inside the body. So you can count on a pretty reliable degradation rate. So basically, because the concentration of water is reliable in vivo, degradation rates are predictable. And this means that you can use polyester devices, for example, for drug delivery vehicles, or tissue engineering scaffolds and things like that. So, but what are some other factors too? Well, if we continue to take a closer look at the chemistry of hydrolysis, there's this K. There's a reaction rate constant associated with this. What effect? So take a moment now, pause and ponder. What effect would temperature have on degradation? Well, temperature, these Ks basically indirectly depend on temperature. And almost always, if you increase the temperature, you also increase these reaction rate constants. So what does this mean? Generally, as temperature increases, the rate of degradation increases. So what does this mean? This means if you're trying to do some sort of like simulated degradation study or something like that, if you're trying to explore degradation phenomena, in vivo, in vitro, things like that, you want to make sure that you do it in a temperature controlled environment so you can understand, so you can basically have a K that recapitulates what the actual Ks that you can experience, in real life. Now, sometimes if you want to sort of predict the lifetime of a device over decades, but you don't want to wait decades to see if your device will last that long, you can artificially increase the temperature beyond what you expect it to be, and then use mathematical models of how temperature might affect K to basically say, hey, this lasted 1 year in this accelerated, in this higher temperature accelerated degradation environment, so I could predict it would last 10 years at a normal environment, something like that. Finally, if you're looking to compost polylactic acid cutlery, it's in New England, where I live, it's very difficult to compost during the winter. Basically, you put your things outside, everything's frozen, it's chilly. These degradation rates are so slow. You got to wait till spring to compost your compostables. So that's the effect here. All right, so thus concludes our closer look at the chemistry of hydrolysis. Let's now look at two modes of degradation, bulk versus surface degradation, and the distinction between them. So bulk versus surface degradation depends on 3 factors. So what 3 factors does it depend on? Well, the first factor is understandably the reaction rate constant. So first we'll talk about bulk versus surface degradation in general. If we talk about bulk degradation, what does bulk degradation look like? Well, imagine I have some blob, some polymeric device, and initially I have a ton of polymer chains. That make it up. Let's say this is a polymer that degrades hydrolytically. Let's say water can diffuse into and through the scaffold, and sort of any of the bonds could break at any time. So basically any bond break at any time. So what might that look like? Well, as time goes on, if all of these bonds are equally likely to break, as time goes on, there's going to be some cleaving of these polymers, and then, as time goes even on farther, more and more of these bonds are broken, until eventually we barely have nothing left. So basically this is as time goes on. So basically, what does this mean? This basically means water can diffuse very freely through the structure and sort of has an equal likelihood of attacking any of these bonds at any time. We might contrast this to surface degradation. And surface degradation is basically this phenomenon where, so here water is basically sort of freely diffusing through the whole device. Surface degradation, basically water attempts to diffuse in the device, but reacts so quickly that it can really only attack polymer bonds at the surface. So what does this mean? This basically means that as time goes on, water continues to attack only the stuff at the surface, and the core remains intact. So core is untouched, and basically the surface reacts. So basically you can almost imagine basically the surface is sort of receding towards the core, where basically the physical device's size gets smaller and smaller and smaller and smaller. So in a sense, basically here, any bond can break at any time. So in this idea, the volume is approximately constant, but the concentration of bonds decreases with time. And here, the volume decreases with time, but within the remaining solid, the concentration of bonds is constant within remaining solid. So what factors affect whether something might be bulk versus surface degradation? Well, it's this kind of race between diffusion and size and reaction rates. So it depends basically on these three factors. This K effective that I talked about, which is reaction rate, constant. It also depends on the diffusivity of water within that material. So this is the diffusivity of water within, I'll just put an H2O as the subscript here, just to signify that this is the diffusivity of water within the polymer. And it also sort of depends on like the overall size, some length scale of the polymer. And for this length scale, L, you can kind of imagine this as sort of like the shortest distance from the surface to the center. So L is basically a length scale, and it's basically the sort of shortest distance from the surface to the core of the device. So basically all three of these factors affect whether we get bulk or surface degradation. So when might we get surface degradation? Well, we might get surface degradation in a couple of cases. We might get surface degradation when, well, so take a moment now, pause and ponder. If we have a very high K, do we expect surface degradation or bulk degradation? So take a moment now, pause and ponder. Would high K be associated with surface or bulk degradation? Well, high K would be associated with surface degradation, right? If the high K basically means the reaction rate is very high, that means that, you know, as soon as that water encounters the polymer, boom, it reacts. So this is basically associated with a high K effective. What about diffusivity of water? So, and conversely, bulk would basically be associated with a low K effective. What about diffusivity of water? Would we expect surface degradation be associated with a high or a low diffusivity of water? Well, surface degradation would be associated with a low diffusivity of water. What does that mean? Basically, if water can't really penetrate very deeply into the material, you know, basically the water diffusion is very slow into the material, then that water is much more likely to react much more quickly than it diffuses. Conversely, in bulk, if diffusion is very high, then it's most more likely to sort of thoroughly have diffused and fully sort of spatially equilibrate in the material. And, you know, if it reacts only occasionally, then it's going to diffuse to the full depth before its likelihood of reacting. So bulk degradation is associated with a high diffusivity of H2O. Finally, let's think about the length scale. Well, surface degradation, you can kind of imagine there's a characteristic depth to which the H2O penetrates before it can react. And if the implant is very large, then sort of relative to the overall size of the implant, we can sort of consider the penetration depth. So basically, for very large objects, we anticipate surface degradation because that water just can't make it all the way to the center. So surface degradation is associated with a large L, a large length scale. Basically, like big things tend to erode versus surface degradation. Whereas bulk, you know, if you have a very thin film of something, that water can fully penetrate to the center. So basically, everything kind of degrades simultaneously. So bulk degradation is associated with a small L. So there we have it for these two. All right, so and it turns out that you can basically combine all of these effects into what's called the second Domkohler number. So the second Domkohler number essentially decides whether we're doing bulk or surface degradation by sort of quantitatively combining all of these, you know, these what's high, what's low all together. So the Domkohler number, the second Domkohler number, is a combination of these things right here. So the second Domkohler number, we give it a special abbreviation. We call it DA with the subscript Roman numeral 2. And it's equal to the following. It's equal to this K effective divided by D over L squared. So it sort of incorporates all three of these parameters here. If you just want a quick refresher, the units of K effective, remember we said was sort of like a 1 over seconds, right? It's kind of like a 1 over half-life. If you dust off your quantitative physiology notes, diffusivity, remember, has units of meters squared per second in SI. And of course, a length scale would have units of meters. So take a moment now. What are the units? Pause and ponder. What are the units of second Domkohler number? Well, if you figured it out, the units of second Domkohler number, it's actually unitless. And in a sense, it's sort of a ratio of how quickly the reaction compares to diffusion. So take a moment now. Think about bulk versus surface degradation, and which one has a high Domkohler number and which one has a low Domkohler number. Well, surface degradation, again, remember we said surface degradation, the thing reacts before it has a chance to diffuse all the way to the center. So surface degradation is associated with a high second Domkohler number. And conversely, bulk would be associated with a low second Domkohler number. And there's not a hard cutoff as to like, you know, what it would be, you know, what exactly constitutes high versus what exactly constitutes low. But, you know, if something's much, much greater than 1, you could say it's surface. If the Domkohler number is much, much lower than 1, then you could say it's probably bulk degradation. Why do we care about whether something is surface versus bulk degradation? Well, this allows us to sort of predict, for example, if this were a drug delivery device, the rate that the drug would be delivered to the patient is very different in this mode compared to this mode. It turns out that surface degradation can sometimes elute an almost constant rate to the patient, and then once it's fully degraded, it stops delivering any drug. And it turns out bulk basically delivers a lot of drug at the beginning, and then it kind of slowly tapers off. And, you know, under some circumstances, we might want one delivery rate, and under some circumstances, we might want the other. Also, maybe for structural things, you know, here we sort of have this continually degrading structure. Here we have the core properties remaining the same, but the geometry is changing. We might want a difference in terms of, you know, one versus the other in terms of whether we want the mechanical properties to be changing or the geometry to be changing as a function of time. So, you know, depending on your application, you know, you might want surface versus bulk degradation, and it's useful to have a way to predict, you know, how drugs are going to be delivered to the patient or how a structural implant is going to change versus time, something like that. So, finally, let's now take a look at the chemistry of materials and make connections between this. So we already took a look at the chemistry of materials and saw So now, let's take a closer look at the relationship between material chemistry and diffusivity, and, you know, sort of eventually the reaction rate. So let's talk a little bit about sutures. So we'll do so in the context of sutures, or what you might call stitches. So if you get a large wound, you know, let's say I got a large wound on my hand, and it was sort of too big of a wound for like a Band-Aid to hold together. If this wound is very large, then a surgeon or ER technician or someone might come in and use sutures to stitch that wound together, right? And the sutures will basically hold that wound in place. For surface wounds, you know, it's pretty easy to then go back a couple weeks later and have them snip the sutures and pull the sutures out. But particularly for internal wounds or something like that, it's good to have these be biodegradable. So either if you don't want to bother the patient coming back for, you know, a stitches removal procedure, or if you're doing internal sutures and you don't want to open the person back up to take out the stitches, you know, this can be good if biodegradable. But they're only good if they're predictably biodegradable. So what do I mean by predictably biodegradable? Well, if the stitches degrade too quickly, then the wound won't be fully healed and it risks opening back up. If they degrade too slowly, then I have these sutures in there, forever, right? Like what's the point of them being biodegradable if they're not going to biodegrade, some reasonable time after the wound has healed? So it's best if these are predictably biodegradable. So what does that mean? That would be nice if we can tune, right? It would be nice if we could sort of change something about the material properties of the stitches or something like that, so we can sort of tune the biodegradation rate. It turns out that stitches are made of a copolymer, and it's a random copolymer. It's a random copolymer of polyglycolic acid and polylactic acid. So these biodegradable sutures are made of a copolymer of these. What does polyglycolic acid looks like? It looks like, it looks like this. And I guess if you look at sort of the edges, right, this and this and this, these make up the ester bond, right? This is a polyester. It's a polyester. Polylactic acid looks very similar to polyglycolic acid, and in that it looks like almost identical. The one tweak is that there's a methyl group. There's a methyl group right here. So again, it's it's a polyester in the same way that polyglycolic acid is. It just has this. So if we're thinking about making a copolymer, a random copolymer, I basically have some fraction of my monomers as polyglycolic acid. I have some fraction of my monomers as polylactic acid. So take a moment now and sketch. On the y-axis, we'll put time to degrade. And on the x-axis, we'll put the fraction that's polylactic acid. So this is PGA and this is PLA. So the fraction polylactic acid, right? We could start with 0, which is all polyglycolic acid, or we could have 1, which is all polylactic acid, and then on the y-axis, put the time to degrade right here. So it's this is essentially like the inverse of your K effective. So just take a moment now, pause and ponder, and sketch what you think this curve might look like, going from all polyglycolic acid to all polylactic acid, taking into account, spoiler alert, the idea that the composition of these is related to the diffusivity of water. All right, so I'll sketch the curve. I'll sketch the curve out. Are you ready for it? It starts out right here when you have all polyglycolic acid. And then as you start to include lactic acid, the time to degrade actually goes down. It starts degrading faster until we have a solid mixture. And then once we start to get up to polylactic acid, it goes back up again. You might be like, what? What's going on here? Well, there are a couple of key features here that I'd like to explain. So, if we have all polyglycolic acid, what microstructure could we expect? Do we expect it to be amorphous? Do we expect it to be semicrystalline? Well, if we have pure glycolic acid, all of these monomers are the same and they can all pack nicely. So when it's all polyglycolic acid, we can basically get a semicrystalline microstructure where basically everything can pack nicely. We get a semicrystalline microstructure. Similarly, if we have all polylactic acid, we also can get a semicrystalline microstructure as well, right, when we have all polylactic acid. But if we have a random copolymer of polyglycolic acid and polylactic acid, they don't line up, right? We have one chain and another chain, and the methyl groups stick out on one chain, they stick out on another chain, but they're not always sticking out in the same place, and those chains can't pack very nicely. So we end up with amorphous. We end up with an amorphous structure down here. Now, why might the time to degrade be really low for an amorphous structure? Well, this basically makes it really easy for water to penetrate the gaps. Basically, in a semicrystalline microstructure, they hold very tight ranks. It's like the movie 300, where the 300 Spartans all have their tight shields all together, But then here, it's amorphous. They're loose ranks. The water can basically sneak in, and it can start attacking all of these. And basically, if the H2O can penetrate the gaps, then it has access to degrade more of the monomers at the same time. Now, one last feature that I'd like to draw your attention to is this right here. If I were to take this line and sort of extend it over here, all polylactic acid takes longer to degrade than all polyglycolic acid, right? So why is PLA slower? Well, why is PLA slower? Well, it has to do with this methyl group. Does this methyl group which one do you think is more hydrophilic, polyglycolic acid or polylactic acid? Well, this guy has the methyl group. The methyl group makes it hydrophobic. And that basically makes it more difficult. So H2O is repelled. That basically makes it more difficult for water to penetrate in, and that basically makes it makes polylactic acid take a much longer time than polyglycolic acid to dissolve. But even so, even though polyglycolic acid is more hydrophilic than polylactic acid, if you have a mixture of the two, it basically totally drives it down by transitioning the structure from semicrystalline to amorphous. One final thought is this the polylactic acid. Take a moment now and think about tacticity. Can polylactic acid exhibit tacticity? Well, yes, it can. Right? This methyl group can either stick out of the page or into the page. So it basically determines on, there can sort of be what's called L or D lactic acid. There's a handedness or a chirality to this carbon right here. And if you have all L or all D, so this is basically all L or all D lactic acid, you end up with something up here. But if you have a mixture of L and D, then they still can't pack quite so nicely against one another. So basically, if you have all poly-L-lactic acid, that forms something that's very semicrystalline because all the chains can pack nicely and it degrades really slowly. But if you have a mix of L and D, then it doesn't quite recover, and actually you can, this mixture of L and D lactic acid could actually degrade more quickly than pure polyglycolic acid, basically with this sort of amorphous effect being a little bit stronger than this hydrophobic versus hydrophilic effect. So hopefully you've learned a little bit about the degradation of polymers in terms of the reactions, whether they're hydrolytic or enzymatic, and that there's such a broad range of reaction rates between these. We took a closer look at hydrolytic degradation and how if you increase the concentration of water, that can drive the reaction towards cleaving those polymer bonds. And there are effective rate constants associated with that degradation. It turns out the rate constant, but not just the rate constant, but also diffusivity and the overall size of the implant affects whether you're in a bulk or surface degradation mode. And the second Domkohler number can help you predict between those two. And then there are some aspects of material chemistry that affect not just the reaction rates, but also how H2O can diffuse within the water and have an indirect effect on the degradation rate. So thank you very much for watching, and good luck with your study of biomaterials.